Yeah, so thanks for the intro, very much and appreciate it. Thanks for the kind words. Yeah, in fact, large-scale memory is getting to a point where it's not large enough anymore for the large language models. And I'll get into that. I'm first going to go into a few definitions because ultimately I'm not sure if everybody is aware of what really all that means and what the impact is and what the requirements are when training and when inferring. The other issue here is I have derived everything from public sources only. We looked at the source code that there is, but I'm not quite sure if the source code for OpenAI's GPT-3 is in any way, form, or shape what in fact they've used. It looks like there's a lot of discrepancy in between what's out there in the open source and what they're using. We couldn't quite reconcile it, so I sort of tried to reverse engineer whatever there is and derive our results from all the information that's out there in the public and see, hopefully, if that matches up with the reality. But in either case, we will see a whole set of new requirements for memory. So what is a large language model? In essence, a language model is a probability distribution over sequences of letters, of words, but of course, in this case, it would be much more complex, even not just words, but also sentences, paragraphs, very likely entire articles and books. And a lot of people assume it's all brand new, and in reality, it's not. So Markov came up with the idea of all of this. That's the same mathematician from which we derive the Markov chains. He defined a language model as a statistical pattern of anything, of a text in a much larger context and text. And then Claude Shannon defined it later in a much more formal way. And so you can assume that the basics of this have been around for a long time. They've been known for a while. The ideas are not new, but the problem is that 50 years ago, or even probably 3 years ago, there wasn't enough compute power and not enough memory available to run anything of that size. And you'd be amazed at the sizes that we're talking about. But let me give you a very simple overview of how the training basically occurs. In essence, you let AI read books. That's the idea, right? And so I'm going to simplify it here. So you look for the occurrences and probabilities of, let's say, the letter A. So just to simplify it all, we're just using the alphabet, capital letters only and 3 letters only, right? So if you look through any text, you will find a certain probability of finding a capital A. And now that you found a capital A, you look at the next one. Right, and so you scan every single document that you can find and throw at this instance of GPT. Now you look for AA, and of course the question is, from an A that we discovered before, what's the likelihood that we find yet another A behind it, or 2 A's behind it? Right? What's the likelihood of an A following an A or a double A? And so we continue doing all of this for AA, AB, AC, and. And so just to make it clear, we are not looking just for letters, because ultimately this would only give us a distribution of letters for the English language. That's not what we're interested in. In AI, and particularly for the GPT, the creators were interested in identifying context. And so it's more like, what's the likelihood of, the word states following the word united, right? Of course, there's United Nations, United Kingdom, and. So it will be very much dependent on what the document is that we're looking through. So you can imagine if you extend this not only to letters and words, but entire paragraphs, what's the likelihood that paragraph A is following paragraph A prime, right? Those are the things that ultimately make up the underlying model for GPT. And you can imagine the more you let this GPT AI instance read, the more you get a representation of all the knowledge available to humankind. Because if it reads all the books that there are, it hopefully has all the knowledge that there could ever be, right? But even that is at this point in time not possible. If you look at the sheer volume of numbers. So GPT-3 was based on 175 billion elements as a training data. And again, these training elements, they were likely not just letters and words, they were books, they were articles, they were everything that we have accumulated in knowledge over the past few hundred years. And so the minimum size of these elements, of course, by definition, is 1 byte, doesn't get smaller than that. The maximum is very likely somewhere in the several gigabyte range, but the likely average is about a megabyte per element needed for training, right? And now the probability of an occurrence, that's at least a 64-bit float. So you could theoretically make up a table saying this word or letter or paragraph is the element that is used to index, and then the probability of the occurrence gives you the likelihood that you would find this particular element being a sentence or a paragraph in all of the books that GPT-3 has scanned. And so this is going to be a very large database if you want to characterize it as a database. And as I said, there's not much info out there, but it was clear to me that this was a very large-scale effort over, well, thousands, maybe more than thousands of servers. But the one thing I found was that training GPT has consumed 1,287 megawatt hours of electric energy. And that's a fairly large number, so you can't retrain it every day. That would take up way too much power and electricity. And it very likely would also clog up all of the Azure backend, because the investment that Microsoft made into OpenAI was mostly predicated on OpenAI's use of the Azure backend for the training purpose. Now, if you look at this, what does it imply with regards to memory limits? And yes, training this is in the beginning an embarrassingly parallel problem. So it's instruction and data parallel. But at some point in time, of course, all of the probabilities for all of the combinations that you found, they have to be combined and consolidated into one large database so that this can now be used as a reference. And so that can theoretically be done by MapReduce, so like Hadoop and applications like that. So they can be used to distribute the processing of all of those elements and then get the results back to be consolidated on one single set of servers so that you can make use of the model. Problem with that is, of course, this is a very large set of servers. And my assumption is it will have taken at least 1,000 servers, if not more. And that's, at this point in time, there's not much info out there. But if you think about it, that's a lot of memory. And an embarrassingly parallel problem usually always runs much, much faster on a machine where the entire memory is unified, where every core has access to the memory, and more importantly, where there's cache coherency across the entire memory. And so we'll look at what the implications of all of that are, and how we deal with a possible follow-up, and how we deal with the fact that the memory sizes keep growing, but the growth of the physical memory and the ability of doing it in a cache coherent way, that is, at this point in time, not quite clear where that path could lead, because today current memories don't support that. And I'll come into why that is the case. Now, if you look at GPT-4, it's even going to be bigger. So we're talking about 1 trillion elements for training. That's 10 to the power of 10 elements at least. And again, if we assume that the average size of an element is a gigabyte, then we end up with a total memory size of 1 terabyte of DRAM. The terabyte of DRAM is if it's with single entry. So that's 1 terabyte already. If we have 1 gigabyte as the average size, then we're ending up with 1 exabyte of DRAM. And the problem with that is there's no single processor and no single computer on this planet that has 1 exabyte worth of DRAM in a cache coherent form. So in other words, the data that is or has to be consolidated at the very end now has to rely on algorithms like sort and quicksort. And so that means that the sorting will first occur locally on the servers that are used to create the training model, and then the sorting has to go across servers. Now, the problem with that is that sort is now basically predicated on the speed, meaning the latency and the bandwidth from one server to another through a network. And that is compared to the speed that has been established today between a CPU and a DRAM, that's incredibly slow, because ultimately from a core, it has to go to the uncore, to all of the stuff that makes up the network on chip, then through the North Bridge, and then in a good case, the root complex for a PCIe network interface card will be on the North Bridge, and then go out onto the network. And from the network, it basically goes back, taking the same path in the server that is receiving the data. So even quicksort, will not work terribly well with the latency-heavy environment that makes up the network. So if we assume that we're now dealing with 1 million terabytes distributed over thousands of servers, tens of thousands, if not 100,000 servers, then the initial run, even if we use MapReduce, the map part will be relatively fast because it's distributed. But then consolidating it all will be extremely slow, because now we have tens or hundreds of thousands of servers that now have to take all the data in and sort it. So not only local sort, but global sort. Now, that's something where you could say, okay, fine, 10 to the power of 12, so 1 trillion elements is roughly 6 times the size of what we have today. But the matter of the fact is, it very likely will not take 6 times, but 2 to the power of 6 times as much time. So that's 128 times the amount of time it takes. And that is a problem, because if we already burned through the amount of power for training GPT-3, then GPT-4 will be exponentially more difficult. So even if we try to do MapReduce to train GPT-4, it'll need 1 exabyte of main memory. There is no cache coherent cluster that can do it. And if we have a look at processors, the current limit for any processor you will find out there is 48 bits of address. So physical address space at this point in time per processor is limited to 256 terabytes. There's nothing out there that exceeds that. And the coherency domain is even smaller. For the most part, the coherency domain doesn't even cover the full physical address space. And so therefore, that's a much lower number. The highest number I found was 2 to the power of 40 bytes is 1 terabyte. And that's sort of questionable, because the cache entries don't seem to be large enough for that. But that's what's being claimed, right? So at this point in time, we have a problem that is so big that we needed exabytes of DRAM, ideally in a cache coherent fashion, for which there's no processor and no memory that exists to support that. And even if we did that, the exchange of coherency information is too slow across a network. And therefore, that's not practical either. So we're looking for something where we have a vastly higher density of memory attached to processors that support an address space that is big enough, that is also part of a coherency domain, and where the coherency domain isn't much smaller than the physical address it can be addressing directly. And so what we can do today isn't by far enough to enable a GPT-4 in a reasonable time frame to be trained, unless we give up on the time frame during which we train and say, well, it may take 100 days or even more than that. And we wait for GPT-4 to be trained with a trillion elements as input data. It's an incredible large amount of data. And unfortunately, as I said, ideally, we would want to do that in a cache coherent server. but there's no memory and there's no processor out there that supports it. So we have to figure out something new. So a new processor, a new memory with vastly larger address space and a coherency domain would be needed to speed all of that up and reduce the energy consumption of training for GPT-4. So again, if we assume that that's not going up by a factor of 6, but instead by a factor of 2 to the power of 6, that would be an energy consumption of 164 gigawatt hours on 128,000 servers. And that's not a sustainable trend, because we would now burn more power than pretty much anything else, any other single application on the internet, just training GPT-4. And that's not environmentally friendly. That's not friendly towards the time that it takes to train it. And even if we later on figure out after it's compressed, even the inference would be very, very slow. Because if we look at that, so the flow chart really is very simple. We take the input parameters, they create the model, and then, of course, the question to ChatGPT would parse that question, try to understand it, apply it to the model, and then create the ChatGPT response. And all of that, of course, implies the size of the model has a direct impact on the performance at which we get the result back, and how much server it needs to run on, and how big this server has to be, not only in terms of the processor cores we have to spend on it, but also the main memory. Because if this server has to fan out the request onto other servers, we again will be limited by the latency and the response of the other servers to this fanned out request. And the latency is an enemy we can't easily overcome. Bandwidth is always easy to overcome, just add more pins. But latency is something that is in the underlying physics. So we can't really go faster than that, faster than light. That's not possible. So as a result, we need something that from a architectural standpoint can deal with a memory of that size and with a response time better than today's systems. So now, even if we look at the inference resource, there's even less information available publicly on how to do that. But the matter of the fact still is that ChatGPT has to understand the question. So it not only parses it, it has to understand it, and then apply that parsed understanding of the question to the model, and then it generates the response from the existing model that there is. And this is even just the inference is computationally rather intense compared to other inference we've seen in AI. And so the question is, how big does the machine have to be and the memory have to be to make this a near real-time experience for the users? And I don't know if you've played with ChatGPT, but sometimes it takes forever to create the response. And you can see it, come on the screen word by word. And it can be fairly frustrating if you see and if you need the result faster. But the matter of the fact is that even on the inference side, it is a very resource-intensive process. And very likely, it takes one server with a terabyte of more DRAM per request. And that's a very large number. That's a very power-hungry server. And at this point in time, if we replace all of the Google searches with ChatGPT-3 searches, it's very likely that we multiply the power consumption of the internet by a factor of 100 or 1,000. And considering that the internet already consumes about anywhere between 4 and 7% of the total electric energy generated, this is unsustainable, because it would be 400 to 700% of the total energy generation just taken up by ChatGPT and GPT training and GPT inference. And so it's not only not sustainable, it is simply not possible. So we have to find out if there's additional hardware that we can develop, particularly processors and memories, with vastly larger densities and the ability to span a coherency domain across all of those memories. That's really what's needed if we all want to pursue the issue of replacing a simple search with a request to GPT and ChatGPT. So that will require a new type of servers and a new type of memory with different features than what we have today. So if you look at it, both training and model data are distributed equally across all the cores. The cores are all symmetric, and in essence, the more it can be made a coherency domain, the faster it can be solved compared to communication, by which you need the core to communicate with another core through a network interface. And so for as long as we keep this in mind, it's intuitively clear that a server with more memory, and it's not necessarily core count, but more memory that is cache coherent, will perform better in any kind of an application that requires a unified model that is as big as the one we expect to see from GPT-4. So, and that's one of the things we're working on. So my company, we're focusing on building a new type of processor, a new type of accelerator, a new type of memory that all can be combined in, in a Lego-like fashion, where we have vastly larger memories with larger coherency domains available for users, including users of GPT, ChatGPT, and GPT-3 and 4, and all of the following versions of it, with the element counts that I mentioned, 175 billion or 1 trillion for GPT-4, and vastly more in the future for that. Anyway, thank you very much.